hydrogens to. Oh, that's a weird way to say it.
Oh, we didn't compare alpha hydrogens to alkyne carbons?
No, but well, the pKa would be the same, but we didn't compare it to nothing.
Compare it to nothing.
Carbon.
Compare it to carbon.
Yeah. We
What
didn't compare
carbon?
it to carbon.
What carbon?
You didn't compare. So the butane, carbonyl. This one versus make it an acetaldehyde. So carbonyl.
I think I'm a little confused. We are not going to consider the alpha carbons of acids, acid halides, acid anhydrides, amides, or nitriles.
Maybe I called it the wrong thing.
We're just going to consider the alpha carbons of aldehydes, ketones, and esters. Those are the three functional groups we'll work with in this unit.
Are they called aldehydes? What are they called?
So, what did you decide? Which of these is the least acidic position? Did you want to add something to that?
What are the two O groups and then nothing in the middle?
Nothing in the middle?
Yeah. Just carbon.
Beta, keto, carbonyl.
But if there's no oxygen there, it's acetaldehyde.
Acid anhydride.
Anhydride. Anhydride, yes.
Beta, keto, or as we decided yesterday, you could call it a beta acyl carbonyl, depending on what your groups are here. But if that's connected by an oxygen, that's an acid anhydride.
I say the least is D, even though of all the alkyl groups, it's the most.
Good. Anybody else agree? Yeah. So would you say there are hydrogens on here that are less acidic than D?
Yes.
Where would those be?
Bottom right.
Bottom right? Here?
Or the one.
Or here? Or here? Or here?
No, just those three because they're the least substituted.
Actually, the more substituted the carbon, the more basic its carbanion. Remember, positive charge sits stable on a more substituted carbon. Negative charge sits less stable on a more substituted carbon. So this would be the least acidic, the most basic carbon in this molecule. It's tertiary, it has no resonance, and it's sp3 hybridized. Then we'd be looking at the secondary carbons. If you wanted to, you could actually say that this is a little bit like an allylic position. So a negative charge there would be in resonance with the alkyne. It would be a weird resonance, but it would technically be able to be in resonance with the alkyne. That would stabilize it, but negative on carbon in those two resonance forms, not super stable. All right, D is the least substituted. What is the most substituted? D is the least acidic. What is the most acidic? Why? Good. So basically, D has no resonance. A has 3 resonance forms, 2 of which put the negative charge on the oxygen. That's great. Now, can we decide between B and C?
Is the third resonance form where the negative charge is in the middle and both oxygens are full?
Correct, yeah. Okay, if a base comes in and deprotonates this hydrogen, the electrons go to carbon. But now, carbon actually has the choice of sharing these into a resonance form with either oxygen. That's what we showed in class on Tuesday, was the form where carbon holds the negative charge, and then the forms where oxygens hold the negative charge. So Christina said substitution helps us determine the acidity between B and C. Does anybody want to work out how the substitution will give us the pKa?
Negative charges want the least substituted, so C would be more acidic, B would be less acidic.
All right, and your reasoning there is based on what we just said about the sp3 carbons.
Yeah.
A more substituted carbon is more destabilized by the negative charge, but here the carbon doesn't hold the negative charge in the major resonance form. So we actually don't consider the substitution
both of them
to destabilize it here.
But both of them have the O group right next to it, like the effect cancels out.
But they are different degrees of substitutions.
Sure.
Anybody else want to reason how substitution will affect this? Instead of looking at substitution of the carbon as providing stability or destability, we should be looking at the substitution of the alkene. There's no alkene right now. When this hydrogen gets deprotonated, the carbon will form a double bond with alpha and carbonyl carbon form a double bond and share the negative charge up to the oxygen. When hydrogen C gets deprotonated, it also creates that alpha to carbonyl pi bond, puts the negative charge on O. There's the alkene. That's the major resonance form, where oxygen holds the negative charge, which means this is where we can talk about stability, not the resonance form where the carbon holds the negative charge. This is a more substituted alkene than this. Di-substituted, 2 carbons coming off of the alkene. Tri-substituted, 3 carbons coming off of the alkene. The more substituted the alkene, the more stable the alkene. So we can rationalize pKa, acidity, by the stability of the alkene resonance form. So this is quite honestly a very confusing thing to say. Typically, the more substituted a carbon is, the more substituted any group is, the better it is as a base, except for alpha carbons, where the more substituted it is, the more substituted the alkene, the more stable the conjugate base.
And to what effect?
To what effect? About 1 order of magnitude. That's what we saw with the aldehydes. So B here would be the next most acidic, which is based on substitution of the alkene, and then C. Did I say it wrong? No, that's right. Oh, it is. I'm sorry. I had it misorganized. This is the least acidic. C is less acidic. Oh man, I didn't mean to be this A, B, C, D. I did that on their midterm. No, I did that on the summer midterm. Did I do it on the midterm again?
I don't think so.
I think I remember you showing me that or something after the fact or before, and I was like, that's mean. But
At least this is backwards. All right, questions on ranking acidity? You will see a question like this on your unit test, and very likely a question like this on the final.
If you broke that bond that forms the 2 rings, would they be the same? C and B be the same?
Yeah. If this was not a bicyclic structure, if it was just a cyclic structure, that would change the substitution of the alkene. They'd both be di-substituted. So that would make a big difference. Great question. Did you have something you wanted to add there?
Oh, nothing. I was just looking at the midterm.
Oh.
You did.
Sorry. I don't mean to do it. All right. Let us work on this worksheet. We've got these 6 structures, and it says show the tautomer forms. Remember, what does tautomer mean? Oh, did I not say it yet? I don't feel like I said it.
Swap it to pi bonds.
We did talk about it? Oh, good. Did I put it on the board at all? Did we write it down?
No.
Let's talk about it.
What they are.
Tautomerization. That was in a different multiverse, James? A different multiverse? You're saying there's a variant of our class?
At the very end of class.
I heard variant.
So did he.
Sorry. All right, tautomerization, the process of converting between tautomers. Tautomers are the ketone to the enol. These are related by equilibrium. These are not resonance forms. Resonance forms simply move pi electrons. Here, there's an entire hydrogen that's being moved. This can be acid or base catalyzed. There's a couple of reactions that we'll see in acid catalyzed conditions, but there's a lot of reactions we'll be using in base catalyzed conditions. Some important things to know. When it comes to aldehydes and ketones, we can use small bases like hydroxide or alkoxides. These we actually call thermodynamic bases. What's the opposite of a small base? A bulky base. Large base or a big base is a good answer too. One of the most common bulky bases that we use, tert butoxide, TBuO-. Why do we say this is bulky? How do you guys use bulky anywhere else other than bulky base? Costco buy in bulk. If you've ever had like a big couch, yeah, it's bulky, it's hard to move. We're going to introduce a new base here, and that new base is LDA. It's very common for people to mistake this with LAH, which is very different than LDA. And these we call kinetic bases. LDA stands for lithium diisopropyl amide. And it does not have an amide functional group. That is the name of the ion, lithium compared to amide. Remember, IDE is a suffix that we use for anions, so the negative charge on a nitrogen from amine becomes amide. So our structure for LDA is this. And remember, compare that to tert butoxide. LDA is actually much more bulky. Much bulkier. Really? Much bulkier?
Yeah.
Oh. Okay.
And it works. It sounds kind of weird, but it works.
I don't know if I like it.
Blame the English language.
When it comes to esters, we cannot create tautomers of esters in acidic conditions. At least not in typical acidic conditions, which is H3O+, aqueous acidic conditions. Let's just show an example of why. When you take an ester and you introduce it to aqueous acidic conditions, H3O+, what happens? From unit 4. Carboxylic acid. This is acid catalyzed hydrolysis. That's not tautomerization, which is why we won't use acidic conditions to make tautomers of our esters. When I say here that we need to have a matching ester linkage, what I mean is that the base, RO-, must be something that matches the OR group of the ester. And here's what that tautomer of the ester looks like. Tautomer of a ketone, cut off one of those carbon groups for the tautomer of an aldehyde, but the tautomer of the ester has an OR and an OH group coming off of it. You might call it a gemetherinol. Gemetherinol? Don't call it Franklin. So, for example, if you have OME, a methyl ester, then you want to use MEO-, meth oxide. What would happen if you had a methyl ester and you treated it with eth oxide? It's not that it wouldn't do anything, but we run the risk of transesterification. Ethoxide, kind of like hydroxide, can react with my ester and substitute the ester linkage. So we avoid transesterification by making sure the base matches the ester. As simple as that.
Well, won't you still form your product?
You form a product. Did you do the post-lab quiz for your project yet?
No.
One of the questions says a student made a mistake. They ran their wintergreen oil synthesis with ethanol instead of methanol as the solvent. Can they still get their product? Can you get wintergreen oil by reacting salicylic acid in ethanol?
You could do, no, but you could do acid and then start over.
You could start over, okay. Same thing here. If I want a methyl ester at the end and I run it in ethoxide and I get a combination of methyl ester and ethyl ester, there's no reason for it. So we want to avoid this condition so that we don't transesterify. I don't know if this is clear. This looks a little unclear. This is a no-no because that runs transesterification. Oops, sorry. That's really ugly.
So the ester will look like this instead of this?
Don't know what you mean. Here is the tautomer form of an ester. Here is transesterification if you use the wrong base. So here's what I want you guys to do. Go through these problems, find the alpha hydrogens, and draw the tautomer. Draw the enol form of these aldehydes, ketones, and esters. If there is no tautomer possible, say that. If there's more than one tautomer possible, show those. do,
I came very unprepared.
but I don't have an eraser.
That's fine. I don't make mistakes.
Well, he doesn't take after me. Yeah, but you can leave it. Just put it in parentheses and say same.
Is it possible for autonomy to have, do they all have to have a double bond in there somewhere, or does
Well,
it?
you have to take an alpha hydrogen and move it to the oxygen. So
Oh, okay.
any alpha hydrogens?
Yes, this one, right?
No.
No, it would, never mind, no alpha.
Good. Carbonyl hydrogen. Aldehyde hydrogen. Not an alpha hydrogen.
Okay, so no carbon there. So you have to have an alpha hydrogen to be able to get a carbon.
You got it.
Okay,
Good.
thank you.
Yep. Great. If you want to, you can put two arrows here. It's equilibrium, please. Yep.
Well, actually, let's be honest. It's the same ones from the shop.
You can
So
put
actually
double
just
bond.
do those. Okay.
For what?
Mm-hmm.
What do you use for
Mhm.
structures?
So you've got
These ones up here are the same as the.
but you lost your carbonyls.
Yeah.
You had two carbonyls, now you have zero. Okay. There you go. Good work. Tricky one. Mm-hmm. Are these different?
We form one or the other.
Are they different?
No.
Right. So it's like you can either give it to me or myself. Oh, that's the same, right? Yep. No, look at try.
This one?
No, I'm just kidding.
Okay. I was like,
So mean.
Good work. Oh, can I put it this way?
Sure.
Good. Good job. Can I see this side? Good.
you want us to draw the alpha hydrogens and also do the tautomerization?
You don't have to draw the alpha hydrogen. Just show the tautomers. Are these different? Right. Mm-hmm. Exactly. So you could maybe say same as instead of or, just to say depends on your perspective. And then on the other side, is this the only one? Is this the only one? Draw all possible. We'll talk about how to get the ones you want. Oh, sorry. Can I see
So
what you got?
if you could explain, right? So this is an effect that we have observed, and it's useful in mechanisms.
Right.
So aldehydes and ketones will tautomerize in those with those two types of bases.
Yeah.
Okay. And there are multiple types of small bases that can do it, and way
Yeah.
more.
Yeah.
These are just common.
Yeah.
And it's necessary for our class.
Yeah.
So when you say the esters must be basic to match to ester linkage, what does that mean?
So I said that we can tautomerize in acid or base catalyzed conditions. That's true for aldehydes and ketones. And these are the bases, small bases and big bases. But esters actually can't be tautomerized in acidic conditions because they will just hydrolyze.
Yes. Okay.
But the basic conditions are also more specific. The aldehydes and ketones, they had a lot of conditions, but esters, the base should match the ester linkage.
That's a tautomer on the right middle.
In red,
Yeah.
that's the tautomer. See how the CO pi bond has
Where
become a
did
CC pi bond?
Where'd the positive charge go? Of the base. I know it's in solution, but is it now
Just
just
like a
alone?
sodium ion balancing, a potassium ion balancing,
So now it's alone.
a spectator ion.
So it's alone.
I never show spectator ions.
I know you never do, but now
What's the
now there's a
spectator?
lone positive charge.
No, it's balanced by this negative. Where is the lone positive charge?
But it just
I'm
swapped
ignoring
out.
it.
You swapped out OR with
This
OR.
is catalyzing tautomerization.
Oh, okay. Do you purposely tautomerize things? Are you?
Yeah, so we can get them to react.
Oh, so while it's tautomerizing, it may do something else.
Yeah,
Okay, so they're a catalyst.
that's why I set up there. Tautomerization is catalyzed by bases and acids. That's it. That's it.
Oh,
Can I see your other side? Oh, sorry. Good, good. Oh no. This one is too far away. Actually, these are both too far away. Notice how the tautomer should form a double bond to the carbonyl carbon. So if it helps, you could put a dot where the carbonyl is, and then alpha beta. And then your tautomer should be at alpha to carbonyl. Yours was actually alpha to beta. And then, is that different than doing it on the other side? Are they different molecules? Right. So it's actually just saying the same thing twice. It's not and. It's same as. Yeah. Or you don't have to show it. On this side, I want to see what. Oh, I gave you the.
I printed this.
Oh, okay. Yeah. So we'll see. See if you can find the tautomers for these. Good. No, what you did is right. There's a bunch of possibilities. Yep. Good. Yep. Good. And there's actually one more form in this one. Yes, exactly. Oh, a double tautomer. I wasn't actually planning on that. There's one other form you could have, which is where it's from the center to the left, the ketone instead of the ester. That's interesting. That actually would work. That's not what I was planning on though. Good. And there's actually another one here where it goes. Oh, this one doesn't work. When oxygen has 3 bonds, it has a positive charge. But you'll notice our tautomers are neutral. So actually, it's from the central carbon, the alpha carbon, to the carbonyl, not from the alcohol. That was really sweet. Good. Yep, the double tautomer. That's the one I wasn't expecting, but that works good. And these are the same. Good. Yeah, I guess technically you could. There's no reason you couldn't. Good. I'll show it.
Was that on the?
Yeah.
Yeah. So.
From this to this carbonyl and from this to this carbonyl.
Okay. So.
I wasn't expecting it.
I thought we were doing just ketones and aldehydes. 2 esters.
Tautomerize?
I guess.
Yes. Esters
Yeah.
tautomerize.
Okay, it's on the board. Okay.
It's okay. I know you're new to this.
Yeah. Been a while.
All right. Let me share with you the answers. So we started with this 2,2-dimethyl propanal, which has no tautomers. Why? No alpha hydrogens. Inevitably, though, I get somebody that shows me something like this. What have they done? What have you done? They added a carbon. Yeah, created a carbon out of thin air. MashaAllah, you should become a synthetic chemist. That's an incredible skill. Yeah, CH3 MGBr, followed by an acid workup, followed by PCC to turn it back into a ketone.
Yeah.
Because the secondary alcohol won't tautomerize, the ketone would.
They just didn't
So just take it through a 3-step synthesis, and then you can have the tautomer, right? So essentially, don't have the aldehyde. This was an example of an aldehyde, a carbonyl, that does not have a tautomer. I wanted to show you that because that's going to become relevant later on, and I put that as the very first one to really shock your system. The second one, another aldehyde. This has one tautomer, although depending on who you ask, that is a cis-alkene, and you technically could form it in the trans-alkene stereoisomer as well. The stereoisomers of the tautomers, not something we're really concerned about. One of the reasons we're drawing tautomers is so that we can predict some reactivity that we'll have. So this is why we're starting here. With this symmetric ketone, oh, I screwed that up. It doesn't matter which side you draw from, the carbonyl or the tautomer is the same. So if you drew it twice, I told you to write it as same, not and, not or, because those are not different structures. I like to say that in my OChem 1 class, when we start looking at stereochemistry of alkene addition reactions, and you say, oh, the two groups add dashed or they add wedged, but no chiral carbons form. So when you say both add wedged, both add dashed, you get both products. I'm like, yeah, sometimes I go to dinner with 3 people, me, myself, and I, right? That just doesn't make any sense. Same thing here. Draw it twice if you want to, but recognize they're the same. This one gave us 2 different tautomers. One from the alpha hydrogen on the left, and one from the alpha hydrogen on the right. Any reason that you guys might look at these 2 structural isomers and say one of them forms more readily than the other?
The substitution.
So which one do you think forms more readily?
The top one. Yeah, tri-substituted.
Cooper, do you agree? Killian, do you agree?
Yeah, I would agree with the top one. Why does it have to be an H, or can you have a negative charge on the oxygen?
Well, that wouldn't be a tautomer,
Okay.
because that would be a conjugate base. Really, the difference here between tautomerization and conjugate bases is just whether it's protonated or deprotonated. So tautomer has to have the same charge. Conjugate base can have a negative.
Would the product of that one also just depend though on what kind of base you're using?
Good question. We're going to get to that. So remember earlier I talked about kinetic bases and thermodynamic bases. That is how we can control these products. If you were to try and describe these 2 structural isomers using the terms kinetic and thermodynamic, would you be able to apply that? If not, no worries, I'm going to teach you. What would you say?
Well, I guess it kind of depends, but if you say thermodynamic would be like the easier formed, then in the top one would be easier formed, and kinetic, you could say maybe kinetic energy, add more heat, do the second option.
You've nailed a very important thing. How do you think about thermodynamic and kinetic? You've got it exactly backwards, but you have to come up with a way to think about it, so I like your effort. Christina?
I thought the thermodynamic product is the one that is more stable, but it forms slower.
Not necessarily slower, but it requires more energy. Yeah. I like to remember thermodynamic as the most dynamic product. The highest high, the lowest low. This requires the most energy to form. It also becomes the most stable when it is formed. So in the same way that we called these bases, kinetic and thermodynamic bases, we can call these products thermodynamic and kinetic. Killian, your idea that the kinetic thing, that's movement, that's energy, add more energy to make the kinetic, that must be the harder one to form. It's actually backwards. The kinetic product requires the least amount of energy, so that you don't need a ton of heat, you don't need a ton of thermal energy, all you need is that wiggling movement, just the bare necessity of kinetics, and you can form it. This requires the least amount of energy to form, but it also is the least stable when it forms. What base do you think you might want if you want to form a thermodynamic enolate or a tautomer? Yes. Use a thermodynamic base to make a thermodynamic tautomer. Use a kinetic base to make a kinetic tautomer. Then we get to our esters. Can someone recall the name of this ester?
Beta keto ester.
This is a beta keto ester. That's a classification.
Doesn't mention.
What was the common name for this ester? Acetoacetate. Because it's an acetate ester, a 2-carbon carbonyl, that is substituted with an aceto group. Oh, God. It's like they really dug into their crazy belts to figure out what they could call it. Specifically, this is ethyl acetoacetate. The lab that you guys are doing in 2 weeks when you come back from Thanksgiving break, ethyl acetoacetate is one of your, oh, maybe I'm wrong. No, I think we got rid of the lab that uses ethyl acetoacetate. Sorry. Yeah, it doesn't use this.
10 minutes.
Ethyl acetate is a very common solvent, and it has mistakenly been put on reagent carts. Or this has been put on reagent carts instead of ethyl acetate, because this is labeled as ethyl acetoacetate. So ethyl acetate doesn't get put out on accident. Anyways, Maddie? Beginning. Yep. You always say alkyl ester. Okay, there were 3 tautomers that I was expecting, but some of you went even further. If we tautomerize from the left-hand side, then we form an enol with the alpha carbon of the ketone. If we tautomerize from the inner alpha carbon to the ketone, then we get this tautomer. And then we can tautomerize from that inner alpha carbon to the ester side. And what some of you showed me was tautomerizing both of the carbonyls from both alpha positions. I hadn't considered it, but I think technically that would work. What would need to be the catalyst for these tautomers? A base. What base?
Any of them. Let's say
It's specific.
thermodynamic base.
Not specific enough.
Oh,
Ethoxide. Because I have an ester, my base has to match my ester linkage. So the base here is ethoxide. You can write that as the carbon chain O-, or you can write it as ET-O-. Great. In the last one, we had oh yeah, let me ask you, what was the name of this ester? Malonic ester. This one would specifically be called with that alkyl group in front. Methylmalonic ester. Yep.
Just assume it's equal.
Yeah, you could call it dimethylmalonate.
Could you say? There's no way to right methyl left ethyl.
Well, it's
malonate.
symmetric, so it wouldn't matter if it's on the right or the left, but you could call it, if you had 2 different alkyl groups, you could call it ethyl methylmalonate, or whatever alkyl group you need. Do I need to draw it twice, the 2 structures? No, because just like the ketone that we had up here, they would be equivalent to each other. And what base would I need here? Methoxide. So you could write that as CH3O-, which would be the same as writing MEO-, which I guess would be the same as just drawing a line to O-. All right, let's dive into how these thermodynamic and kinetic bases work. Are you guys okay if I clear away this side on the bases?
Can you explain the transesterification? Does that just mean you swap out the group?
Yeah, so if you have an ester with our group methyl, and then you have ethoxide come in, ethoxide acts as a nucleophile, breaks open the carbonyl bond,
Oh yeah.
and then it has a chance of
Yeah, I
kicking
see.
off OMe. It also has a chance of kicking off OET, which just came on. But you get transesterification, which is something you want to avoid. All right, let's look at this two-way reaction coordinate diagram. Along the y-axis, we plot energy. By the way, I need to send out an email about this. I'm giving a talk on Monday about energy. It's a STEM fun talk, and I love energy. I think it's so fun. So we're just going to look at what energy is and all the ways it shows up.
Can we get extra credit for going?
No, thanks for asking. Monday at 2 p.m. in the Technology Building 104. This is the worst part. I'm gonna invite you guys all to come. I'll send out the flyer, but I am not getting extra credit. I think the math students are getting extra credit because this used to be a math department thing. The math department was doing math fun talks, and then they infected this whole STEM school, and now everyone is giving fun talks. But their students are still being encouraged to go. I'm sorry, I don't. The only way I'd give you extra credit is if I asked you to show me that you learned something from it. And I don't know what I would ask, and I don't know if I want to grade it.
I mean, in the math classes though, that's usually like your only way of getting extra credit.
Okay, fair enough. I don't need to.
For your class, you have options.
You have options.
You also pay your students though, because you don't give them extra credit.
I try. I do my best.
Yeah.
All right. In red, I'm going to use thermodynamic bases. In blue, I'll use kinetic bases. When this ketone reacts with a small base, like sodium hydroxide or sodium methoxide, some small base, the product that forms is the thermodynamic enolate. Now, I know I'm showing the enolate and not the enol. Yeah?
Wait, one second.
Okay.
You said it makes the thermodynamic.
Right.
Isn't that the kinetic?
Nope. You don't really have anything to compare it to yet, but I'm going to make a smaller hump and a higher product on the right-hand side.
That's fair. Yeah. I'm basing off of my old notes in your class where you had it on the opposite side.
I just flipped the side,
so-
and I flipped the colors.
So now I'm like, okay.
Sorry.
Nah, you're good.
On the right-hand side, I'm going to show when this ketone reacts with a big bulky base, like tert butoxide or LDA. Once again, I know I'm showing the enolate and not the enol. I wanted you to practice with tautomerization, but for the most part, we're going to be using the enolates as reactive intermediates, not the enols. This is the kinetic product. And you can see the energy difference. Thermodynamic has the highest high and the lowest low. That's why I like to call it thermodynamic. I don't know if they had a better reason for it when they assigned those, but that is what I use. Once again, we're looking at the stability of the alkene. So, can someone justify the energy of these transition states?
So it,
Why is the transition state with the kinetic base so much higher than the transition state with the... Sorry. Why is the transition state for the thermodynamic base so much higher?
could carbon be resisting change more than hydrogen? Carbon's electrons.
Same amount of carbon and hydrogen changing. Sterics. Sterics is the answer. For a base to take away a hydrogen from the more substituted position is harder. It takes more energy, despite the fact that the pKa is lower. But we rationalize the pKa is lower because the conjugate base is also more stable. It is harder to take that hydrogen from a tertiary position. And we've already rationalized why this product is more stable. Technically, we would call this electronics. The pi bond is stabilized. The electrons of the pi bond are stabilized when it's more substituted. So if you wanted to, you could point at this and say, this is destabilized by electronic sterics. This is stabilized by its electronics. I don't say this enough, but my OChem professor once said that everything in organic chemistry can come down to sterics and electronics. But actually, sterics is electronics. What are we talking about when we say steric strain? Yeah, you've got more electron density pushing against the electron density coming in. That's actually just electronics. So everything in chemistry is just about the electrons, except for nuclear fusion, right? At that point, the electrons aren't what's relevant. Okay, so now we have it. If you want to make one enolate over another, then you can have regio control. Tell me though, of our aldehydes, ketones, and esters, which of these really have regio control? Which do I need regio control for? Just ketones. The aldehydes, there's only one tautomer that forms anyways. Ketones, there can often be two different tautomers. Esters, I guess the only esters I gave you were kind of these interesting cases where it's a beta keto ester. But esters also, just like aldehydes, only have one alpha hydrogen position. So I don't need regio control. This is all regio control for ketones. Aldehydes and esters don't need it. So why might I use tert butoxide over LDA? Like, why do I come in here to introduce a new bulky base to you at the end of OChem 2?
What was the question?
Why do I give you a new base?
Wasn't there like a tert or the tert propyl group in the LDA too?
You mean diisopropyl?
Yeah.
Yeah. So what? But why?
No, I don't.
let's look at percent enolization. Or, in other words, percent tautomerization. Different bases give different effects on the equilibrium. Let's take an aldehyde, something like acid aldehyde, and let's react it with sodium hydroxide. This gives the enolate or the enol, so the tautomer, at a ratio of about 99 to 1. Actually, I'm sorry, I think this is more like 95 to 5. This small base is not very good at doing tautomerization. Let's take this same ketone and let's look at tert butoxide. Tert butoxide, although it gives us regio control, it also gives us this 95 to 5 enolization. So you can put an H on the top. That would be the enol. This is the enolate. It's just its conjugate base. The difference is simply whether this finishes the catalysis. You can put it on there if you want to. Again, I'm slowly shifting us from tautomerization to just the enolates, because these will be the forms that are more reactive for us. Similarly, if I ran this alkene with a small base, or sorry, this ketone with a small base, let's switch it from sodium hydroxide to methoxide, where now I get the thermodynamic. I'm still looking at 95 parts to 5. And lastly, let's take an ester. Esters, as you remember, are the least acidic of the groups. And so the percent tautomerization here is even worse. This is about 99 to 1. A reaction occurs, but in terms of equilibrium, nothing's really happening. So if I wanted to be able to react using an enolate, we're going to use enolates as nucleophiles. I want to create a lot of my nucleophile. I don't want 5 parts in 100 to be my nucleophile. I want 100 parts to be my nucleophile. Sometimes we can take advantage of that. Sometimes we want to modify it. So let's change this now to look at each of these reacting with LDA. You guys okay with that flowchart? Instead of 3 separate lines, it's just saying that they all are reacting with the same thing. We always get the kinetic base, or the kinetic product, but that only applies to this ketone. The other ones, there's only one enolate anyways to form. But now the ratio flips. We're left with 1 part to 99. And actually, most people will tell you that this is more like 100%, approximately 100%. Complete enolization. For ketones, it's regiospecific. You don't have any control over that. But that means that you don't have a mixture of both your starting ketone and your enolate. You've got just this structure. So we're going to use that to our advantage in some of our reactions. But this is a good time for us to take a break. Get up, stretch, move your legs, and then we'll come back in to look at our reactions.
Does Utah get more light than Wisconsin?
I think Utah is further south than Wisconsin.
So we get a little more. So your family went dark like a week ago.
Went dark.
I feel like at the same time.
Wisconsin's not real.
Oh,
It's true. I've been there. There was water everywhere.
his
All the
dad's
grass
from
was
there.
green. There was a whole hill, and there was not a single yellow spot on that hill. Of all the grass was alive.
Even
It-
though Finland's also not real. That's an actual conspiracy theory.
I thought it was Australia.
That's probably another one. But yeah, no, there's one that Finland's not real. It had to do with like the Soviets and the Japanese sharing it as like a secret fishing spot or something.
Huh.
I don't remember what it was. It gave me a headache when I was trying to read it and understand. But
Strange.
Any places you don't think are real?
Finland.
No, I really do believe Finland is real. And
I mean, like you, at first I was like, no way, that's true. But the more you read, the more you realize it's true, man. The deep state's trying to keep Finland from you.
Isn't it the Soviet state?
The Soviet deep state.
Yeah. Naomi. Wow. You got you fit Naomi in her whole reaction.
Yeah, John, I like don't remember this chapter. Like, I can do it. It makes sense, like in my notes stuff when I'm like looking at it. But it's just, and it's really weird because you'd think that this would be the one that would stick with me because it's the most recent one I learned.
He didn't cover nitrogen reactions with you?
nope.
You know, I bet in a few years you'll be able to get there.
I actually, my first semester teaching, I did do it.
Oh,
My first semester teaching OChem 2, I taught the nitrogen, the amine chapter.
what happened?
It was boring and useless. And
I mean, it also, it's still pretty similar to, like the mechanism that I was trying to figure out with Kayla, I asked you about, like, while I did it wrong technically, I still did it right. And that I did all the steps, like, right, basically. It was just the wrong acid.
Right, yep.
So, like, it follows very similar steps. So, like, if you can do the, like, hydrolysis and stuff, or, like, those things, you can do the other one.
that's why I have started refining the mechanisms. I also used to say that every reaction we see is fair game for a mechanism. And then I was like, oh, that sucks.
Yeah, that sucks. That's mean.
Yeah, it is. And it's useless.
Hey, but
Students learn less.
that being said, you admit that and then you grow. Unlike my chem teacher who doesn't admit that. And then I looked up her reviews.
She doesn't want to grow, though, either.
Yeah, no, she's mean. But I looked up her reviews. They're all from my class. It's like very obvious because this is her first semester at the U.
Right.
It's like
Oh, right,
her,
right.
Her like previous reviews were like also bad from like her other college, but this was her third. It's just 1 star, she just has like 10 reviews. They're all just one.
And you know what? When it comes to her like tenure committee, they'll be like, maybe if you get a chance, try to do better in your classes.
She's also probably one of those professors who is like,
Whereas if I got 1 stars, my tenure committee would be like, I think we're gonna let you go.
They rate your professors?
I don't know, but they definitely look at my
It's like-
course evals, and the course evals will match. I gotta grab a soda quick.
can't fun.
Just gotta grab a soda. I thought they call it pop up there.
It was great. I need remediation. I don't want to read this. Like it makes sense. Like when I'm seeing this, is like it's coming back. And like I remember when I look at my notes, but it's the more it kind of sucks when I'm trying to tutor it. I'm like, all right, 1 sec, let me go and like relearn this real quick. But except there's a really good trick for that when you're tutoring is basically just be like, hey, hear me out. This might be the right way, and then you just now you can get it wrong because you gave them that disclaimer that might work.
Yeah.
So I think
Legally can't see.
True, and then it's like always the case that they're like
so I what?
the case.
That it's wrong or that it's correct? Cool.
No, that's correct.
What the
Got the ball blast.
Yeah, I started going to the gym in the mornings, and I have a very, I had a very small lunch today, so I'm feeling very hungry.
You should have got more pizza.
Don't tell my partner I'm about to go home and eat.
What?
What questions do you have on this?
Yeah, we see them all the
On
time.
which that?
Yeah, the percent enolization.
Why does LDA make it almost like a complete flip?
Love that question.
Can you draw LDA again?
I will actually.
Latter day
Let's dissect this.
Anglicans.
No.
For those reactions with oxygen groups, we have some carbonyl plus OH minus. The other side of this equilibrium is some enolate plus H2O. For those reactions with LDA, I have some carbonyl plus diisopropylamide in equilibrium with some enolate plus diisopropyl amine. That's why.
I see.
Really?
Yeah, because looking back from like our carbonyl derivatives, water would readily react with.
So let's. Oh no, actually, it's not about the reactivity. It's about the pKa's. Remember what the pKa was here. This is my acid. What's the pKa of my acid here?
25.
Yeah,
Oh, well,
25 on the high end,
35.
15 on the low end
Um,
for this acid.
this is true.
Thank you. What is the pKa of my acids on the right? Water is my acid on the right.
14.
pKa is not 14.
7.
Other way.
28.
No.
21.
It's close to 14.
8.
pKa of water is very close to the pKa of alcohols, and the pKa of alcohols is around 15 to 18. Water is about 15. I think it's 15.6. What is the pKa of an amine? No, nothing has a pKa of 85. 55 is in the range of alkane carbons. And amines are much more acidic than that because nitrogen is more electronegative. Amines have a pKa around 35. These acids that form are not the same. They're not even in the same wheelhouse. What's a better acid? Something with a pKa between 15 and 25, or something with a pK of 15.6.
15.6.
If that's a better acid, then it does its job better. If it's a better acid, then it's not an acid. Does that make sense? If it's a better acid, it exists as its conjugate base. Also, I'm really proud of you guys for saying that so quickly and in harmony. That was really great. What's a better acid? Something with a pKa from 15 to 25 or something with a pK of 35?
15 to 25.
If it's a better acid, then it does its job better, and it doesn't exist. We've flipped the equilibrium. Maybe it would help if I drew my arrows the opposite size so that you can see. Now, equilibrium prefers forming the enolate and the amine. The amine is not a very good acid to protonate the enolate. So actually, I was showing tautomerization before. Actually, the LDA will not finish that tautomerization. It won't give this hydrogen back. When you compare equilibrium, you can actually take the pKa values to the power of 10 to show the difference in the equilibrium. Sorry, the difference in the pKa values. So here the equilibrium is somewhere from about 10 to the 1. You know, if I have a very acidic group, to 10 to the 10. That is the equilibrium distance. This side is favored about 10 to the 10 times, or 10 to the 1 times. But this side is favored. The equilibrium distance here is from 10 to the 10 to about 10 to the 20 times, favoring these products. There's this huge equilibrium shift to the right-hand side. What I mean by these numbers is for every 1 molecule of your enolate, you have 10 to the 10 molecules, for every 1 molecule of your carbonyl, you have 10 to the 10 molecules of your enolate. For every 1 molecule of your carbonyl, 10 to the 20 molecules of the enolate. So this is what we call complete enolization. All right, let's look at our reactions. We've got this sheet that gives us some. The first reaction, we'll take this unequally substituted ketone, and let's run it through radical halogenation. Br2 with light. Do you remember why we represent light as H nu? Planck's constant and the frequency of light. I think it's when you multiply those, you get the energy of the light. E equals h nu. Also, E equals c divided by lambda times h. hc over lambda. So it's easier to write h nu. This is going to form a radical intermediate. Where do radicals prefer to go? More substituted or less substituted?
Alkene.
Radicals trend with carbocations. Carbocations prefer to be more substituted. Radicals prefer to be more substituted. So this is going to go to the more substituted position.
How do you know?
Okay, we can prove it. Well, you have to look at the radical, though. It's a terrible bromine, isn't it? It's not much better. So, regio-specific. If you want to see the reaction, remember that in the first step, what light does is it cleaves the bromine-bromine bond to give us two bromine radicals. The first bromine radical abstracts a hydrogen, and it's going to abstract the hydrogen from the more substituted side, because that leaves you with the more substituted radical. That gives us HBr.
Why would
And
the
this.
why would
I'm going to tell you why it likes the more substituted side, if you'll give me a second. This one I can really prove it to you. If it's not next to a carbonyl, if it's not an alpha position, it's a little bit harder for me to prove it to you. This is in resonance. That's why regardless of what there is going on in the structure, this is actually always going to prefer to go to the alpha position. Because then it can be in resonance with that alpha position. The resonance has these fishhook arrows. One of the pi electrons from CO comes to meet the radical and form an alkene. What substitution of alkene? Why, the most stable, of course. The more substituted alkene. Don't forget that we still have this bromine floating around. If there are two resonance forms, one where carbon holds the reactive electron and one where oxygen holds the reactive electron, which resonance form is more reactive? Which resonance form is more stable? Okay. Anybody want to back up Christina's claim?
No.
Back it up.
I don't know. I was just being contrarian. I haven't even thought about it. I spaced out.
did you say the oxygen was more stable?
Carbon?
Christina is saying oxygen holds the electron more stable, carbon holds it more reactive. Meaning, one of these resonance forms looks like the structure a majority of the time, a major contributor, and one of the structures is more reactive, more likely to be the one that performs a reaction next. Killian?
Well, I would back it up by saying that oxygen holds onto its electrons more, so the carbon one would be easier to take.
Good. Carbon is less electronegative, more willing to share electrons, more reactive with the electrons. More reactive, more stable. So if I want to show this second step happening, it's going to happen from the more reactive side. I don't need to redraw the earlier resonance form, but I can't double up on this. I can't show this resonance form, making this product, and then go back to this resonance form and showing it react. But remember, any resonance form is the same exact structure. So any step of a chemical reaction that's happening next can be shown from any of the resonance forms that exist. So from this resonance form, I will reform my CO pi bond, and then I will have a termination step. This CC electron comes to meet this bromine electron, the creation of a sigma bond.
Does it react at that step because the oxygen wants that other electron that the carbons have?
It has it.
Yeah, it starts with it.
And don't forget, Killian, that this is not what the molecule looks like. This is a lie. I hate lying to you. I don't want to lie to you. Don't make me tell you the truth. If you remember, this is a pi system.
Stop it now, please. I don't want MO theory.
MO theory is the truth.
I don't like the truth.
There is a pi bond in this molecule, and there is a radical electron. That radical electron occupies an orbital that sits over the oxygen and the alpha carbon, but not the carbonyl carbon.
Huh.
These do not exist. It's a lie. I'm sorry. It's not my fault either. I wasn't smart enough to come up with this on my own. I don't know. Yeah, I think probably. We can blame Lewis. So the question is not oxygen wants to pull these electrons back. No. It has that electron already. It has all of the electrons. It is both of these at the same time. You might even show it as this resonance hybrid. Where you've got single bond, radical electron. Or I think maybe what you'd have to show is dotted line resonance electron. Okay? That's even misleading because it makes you think the carbonyl carbon also has that radical, and it doesn't. All right. Did we all get that this was regioselective? Prefers to go to the more substituted position because of the more substituted radical. Our next reaction is acid catalyzed halogenation. H3O plus and X2. Let's look at an example where we use chlorine. This reaction is also regioselective. Those of you that took Gen Chem 2 lab here, you ran this reaction. You took acetone, iodine, and hydrochloric acid, and you studied the kinetics of it. You found that the kinetics were dependent on iodine and acetone, but not dependent on the catalyst, HCl. This is alpha-halogenation in acidic conditions. Regardless of how many equivalences you do, if you have an excess amount of halogen, this is the only product you will get. You will only ever get a monohalogenated product. There's a reason for this. When the acid tautomerizes the ketone, and then the ketone tautomer, the enol, takes on the halogen, it makes the whole structure less acidic, less basic. So this is less reactive to the acid than the starting material was. The alpha halogenation changes the electronics the reactivity of the structure and makes it less reactive to acid, so you only ever get a monohalogenated product. If we run this with base, let's show first hydroxide and a different halogen, bromine, or sorry, different halogen, iodine, I2. Because the hydroxide is a thermodynamic base, the enolate that forms is on the more substituted position. And because that more substituted position only has one hydrogen to give, this is our product. Let's modify this. We're going to do a reaction with tert butoxide and Br2. And again, we're going to have these in excess. I forgot to say that we'll have excess here of the iodine as well. Now tert butoxide takes us to the other side of the ring. And because there are two alpha hydrogens on the other side of the ring, both of those alpha hydrogens become halogenated.
Are they in excess to push equilibrium, or because otherwise you'll get different forms?
They're in excess to push equilibrium, and so that they are the excess reagent, not the limiting reagent. I think I'm realizing that this molecule that I've given you, it's not the best for showing that acid catalyzed conditions will only ever give you a monohalogenated product. Because I'm telling you this is regioselective, and this is regioselective, and there's only one alpha position there. So I think I want to kind of give you an aside to show you. Let's not work with 2-methylcyclohexanone. Let's work with cyclohexanone. And let's do these same acid catalyzed conditions, bromine in excess. We should imagine bromine in excess where there were 2 alpha positions. In base, it happened twice. In acid, it still only happens once. When you take a carbonyl structure and you add a halogen onto it, you change the acidity and the basicity of that compound. So it goes to reason that acidic conditions will have different reactivity with the product than basic conditions. In basic conditions, we form first the monohalogenated product, which becomes a better acid in basic conditions. So then it's able to halogenate again even more readily. But in acidic conditions, you monohalogenate. Now it's a weaker base, and it needs to be a base in acidic conditions. So now it's less reactive, it's monohalogenated. We can control our equivalences by using acidic conditions versus basic conditions. On the bottom, you'll notice that there's another reaction that has benzene and then a methyl group on one side. What we're going to react this with here is excess sodium hydroxide and excess chlorine.
molecule called?
This?
Yeah.
This is called acetophenone. So you see the 2-carbon carbonyl and then the phenyl group, and it's a ketone. What is different about this carbonyl compared to 2-methyl cyclohexanone and cyclohexanone?
Benzene.
Okay, it's conjugated. Let's honestly ignore the fact that it's a benzene. It doesn't need to be a benzene.
You have aldehyde versus ketone.
It's not an aldehyde.
Oh, yeah.
They're all ketones.
Has two separate functional groups instead of one cyclic.
Okay, that's true. Keep going.
Is that you can't form bonds on the left side?
Okay, that's true. Keep going.
Only one
Only one
alpha hydrogen.
position of alpha hydrogens. That's true. Keep going.
It's attached to a primary carbon.
Attached to a methyl group, a primary carbon, as opposed to secondary carbons, secondary and tertiary. That was the key. The fact that this is a methyl group. Here's a product. CHCl3. I've written it in orange to help you track that. The other product that forms here Did you see that? Did you catch it? That is a carboxylate. That's a deprotonated carboxylic acid. So if you are to run this with an acid workup, for instance, if you were to say 1 excess sodium hydroxide and chlorine 2 H3O plus, then your products are this carboxylic acid and CHCl3. What is the functional group transformation that's happening here?
Oxygen.
From what to what?
Methyl group to it.
Functional group.
Ketone to carboxylic.
From a ketone to a carboxylic acid. That is a functional group change we have not seen yet. It only occurs if there is a methyl group attached to the ketone. This is called the haloform reaction. And you can see its name based in one of the products that forms. When you run this with chlorine, you produce chloroform. When you run this with bromine, you produce bromoform. When you run this with iodine, you produce iodoform. This is one of the reasons you should never listen to people on the internet. People on the internet will tell you to go out and buy acetone, which is a ketone with a CH3 group, bleach, which can produce Cl2, and sodium hydroxide, which is just lye. And if you mix those all in a toilet bowl, they'll produce a toxic amount of chloroform, and you'll die. So don't listen to people on the internet that tell you to do that kind of stuff. Also, you guys know what entertainment uses chloroform for? Like in movies.
Oh, to knock people out.
It's a knockout gas. It actually takes a lot of chloroform to knock someone out, and usually by the time you've administered enough to knock them out, you have potentially killed them as well. Chloroform is not something you want to just slap on someone's face and hope they'll fall asleep. It will take way too long, and you'll probably kill them. So this is a reason why household chemicals, acetone, lye, and bleach, can actually cause very dangerous chemical reactions if all mixed together. Very cool. Very scary.
Like vinegar is also really bad for that because people don't realize vinegar's reacting with stuff because it's a food product more so than
Right.
so.
right? All right, I do want to show you guys the mechanism for this. Oh, I didn't plug this in. Because the mechanism is a bit repetitive, but it is very useful in understanding the enol nature of everything. So, what I'm going to do here is show every equivalence of sodium hydroxide and chlorine at every step until it's been used and produced as a byproduct, and then I'll ignore it. So that is, I need 3 equivalences of sodium hydroxide to deprotonate all 3 of my methyl hydrogens. I need a 4th equivalence of sodium hydroxide to substitute the chloroform and leave me with a carboxylic acid. I need 3 equivalences of chlorine to give me the chloroform. In my first step, I'm actually going to ignore Na. In my first step, I'll use hydroxide. Hydroxide acts as a base. Real quick pause. In Unit 4, we learned that hydroxide and ketones can do acyl addition to give us diols. That is a possible reaction here. When I tell you guys that molecules do a bunch of weird stuff and we're just showing a mechanism to get to what we want to show, we're ignoring all the other fun, weird stuff that it can do here. We're just focusing on the chloroform mechanism. Hydroxide acts as a base, takes an alpha hydrogen. I can show either of the 2 resonance forms where the carbonyl holds the electrons, where the alpha carbon holds the electrons, or where the carbonyl oxygen holds the electrons. I'm going to show the oxygen holding the electrons because that's the more stable resonance form. When we're talking about tautomerization, this is where I could have the water be deprotonated by the O- and I create an enol. That would be the tautomer. But this enolate is reactive to more than just water. It is a nucleophile and chlorine is an electrophile. So the O- reforms the CO double bond. I like to say that it collapses. Because we said the stable resonance form is when O holds the negative charge. The reactive resonance form comes from the carbon. Carbon acts as a nucleophile and attacks chlorine and kicks off chloride. That gives me a byproduct of chloride, plus I had a byproduct of water up above. I'm down to 3 equivalences of hydroxide and 2 equivalences of chlorine. I repeat. Now that this structure has been alpha-halogenated, those alpha halogens are even more reactive. Now I have an electronegative group that has an inductive effect towards itself, making these hydrogens even more acidic. They share their electrons to the oxygen. I form another equivalence of water. And I have a second equivalence of chlorine that will act as an electrophile. I'm in my stable resonance form right now. I'll reform the CO double bond and attack from the alpha carbon. CO double bond reforms, alpha carbon attacks chlorine, kicks off chloride. Now I have a dihalogenated alpha position. While you guys copy, because I know it's a lot. It's so fun. I'm gonna circle my byproducts in green. Once again, hydroxide is now even more reactive here because now I have twice as many halogens pulling electron density away from this CH bond. I get my third equivalence of water. I get my third time being in this reactive enolate form. CO double bond reforms. Alpha carbon attacks my final equivalence of chlorine. I get to a trihalogenated product. More byproducts.
So in my notes of this, I don't have it forming the enolates, but just forming a carbanion. So I guess like that's just a resonance form.
Correct.
So yeah. Okay. So this is more, I guess, correct probably, or more.
It depends on how you want to say it, right? They are both.
Yeah.
And I think what I got was from past semesters is most people see the most stable resonance form as being the one to draw. Although I wanted to show you the more reactive one since that's the one that reacts. But either way is pretty good. Now, I want you to consider how trichloro alpha position affects the electrophilicity of the carbonyl. Is the carbonyl a better electrophile or a worse electrophile than it was at the start? Worse? Less electrophilic, less willing to take electrons. Better electrophile, more willing to take electrons. What does it need to take electrons? A partial positive or a partial negative? Needs a partial positive, which it gets because of the CO bond. Its oxygen is pulling electrons. Are the chlorines pulling electrons away from the carbonyl carbon? Or are the chlorines giving electrons to the carbonyl carbon? Increasing the partial positive, pulling electrons. That means hydroxide attacks the carbonyl even more easily than it could have at the beginning. This gives me O minus, OH, CCl3. That is a tetrahedral intermediate. Those tetrahedral intermediates formed all over the place in our unit 4, in all of our acyl derivation products. The CO minus collapses back down into the CO double bond. What is it going to kick off? It could kick off OH. That would just send us backwards. Instead, it kicks off the carbon group, CCl3. This is likely the first mechanism you've ever drawn where you get to break a carbon-carbon bond. Ozonolysis, yeah, that breaks carbon-carbon bonds. You don't usually draw that mechanism. The reason that we can break this carbon-carbon bond is because our carbon holding the negative charge has these 3 strong electronegative groups helping to stabilize that negative charge. These groups are pulling electrons towards themselves, so the carbon is okay to hold the electrons. But the carbon is still a base in the presence of a newly formed carboxylic acid. And so we see a simple acid-base reaction, leaving us with chloroform and a carboxylate. One of the reasons I want you to copy this mechanism down is for the repetitive nature of forming the enolate. You get to do it 3 different times here. Each time thinking about attack the alpha hydrogen, send the CH bond to be a CC bond, send the CO bond to be O minus. 3 different times you form an enolate, and you're going to be doing enolate mechanisms on the final exam and on the next unit test, so this is a good time to practice it. So fun.
You guys done like aldol stuff yet?
No, we're going to do aldol next week.
I was following on
Oh,
like,
and the week
in
after.
my notes, and so like we did it opposite.
Correct.
This is like the last thing in my notes before the final review.
That's right.
So, okay.
I actually have switched the way it goes because it aligns better with active. These reactions down here, you'll notice that we're not taking the aldehyde or ketone route. Instead, we're using the acetoacetate. We could also be using malonic ester. What I'm going to demonstrate down here are alkylation reactions. We're going to take that alpha position. We're going to add alkyl groups. I think this I want to save for next week rather than trying to cram them in 2 minutes. So I guess you're free to go 2 minutes early. Wow, I never do that. Tuesday, we still have class. Thursday, take it off. Happy Thanksgiving. And then we'll come back in the week after Thanksgiving and we will round out the semester with our aldol condensation and Claisen condensation reactions. We're in the home stretch. Correct, yeah. We're in the home stretch. We're almost done. So keep your head up and don't forget to go back and study concepts from Unit 1, 2, and 3 as you start preparing for the final in just under a month. All right? Have a good night, guys. I'll see you Tuesday.
Okay. On this reaction with the H3O, you go through the whole process. It still requires the same amount of NaOHs and CO2s, correct?
And then,
And
once
then
you get here,
again, it just
you just add an acid so that you can pronate that.
wanted to make sure.
You got it.